spaces kind of grow organically. You know, you had a group of people interested in bicycles, so you buy a bunch of bicycle tools, and so there's a lot of that kind of character in there. Fab labs are also shared spaces, but they're designed with a very specific intent to have a specific spectrum of tools that allow you to build almost anything, complete functional systems, from structural components to microelectronics along the way. And so this is a large machine in the Fab Lab, which is a milling machine. These are all computer numerically controlled. So around the corner is a car full of laptops that operate in all the major operating systems and have all sorts of software packages, some open source, which are free, some commercial, which have significant annual costs associated with them. So we try to teach people versions that they can actually take home and run in their basement with no licensing costs, and also what the commercial standards are associated with it. So for example, we run Mac OS and Linux, which is free, and Windows, which is mostly the commercial standard, and then we have a range of packages too. But what we deal with is the interface between atoms and bits. And so bits is the digital world, and so we design things on computer. We also have 3D scanners that allow us to convert from atoms to bits. We can assess the shape of something and produce a digital design file from it. And a lot of these machines are the opposite direction, which is going from a digital design file and actually creating material to reflect that design. At this point in time, we're doing it out of carbon fiber. We need the lightness. We're doing this with high school students. My preference would be to use industrial hemp, but hemp and high school students are kind of cognitive dissonance. Our preference
you
would
get
be
a note from each parent.
Yeah, our preference, no, the newspaper articles is what I'm worried about. So, you know, our preference would be to use green composites, and hemp is actually a tremendous material to be able to make the resins and the fiber. And Michigan is actually moving in a direction to be able to actually do some of that, and so that will integrate into our permaculture program, and we got to let that emerge over time. So we're moving towards more and more environmentally friendly materials. Right now we're trying to prove that it can be done, so we're using, you know, more industrial kind of materials. The point is, you know, a lot of folks use this for sign making and capture making and the like, and we do that also for furniture, but we're also using it for structural components for houses, and also to, again, do molds, to be able to use composite pieces for cars and other types of things.
So does that change your design logic that every piece has to be smaller than 8 by 4 feet? And so you build up from component pieces? Like I noticed the furniture is all these smaller pieces put together.
Well, that's because of the specific modularity for what people are interested in and the shapes involved. And so we could have, you know, done a whole 4 by 8 foot tabletop, but then you'd been stuck with that. A lot of people want a long skinny one, or they want L-shaped one, so that was kind of the unit that was best for that. When we're laying up things, for example, we can do a 10 foot by 6 foot mold and chop it into sections that we can mill and then glue them together afterwards and just lay up that whole piece. So it's not necessarily the case that the eventual design has to have smaller components, but the sub-components that we build to go into it fits within the machines. There's a picture over here of an abrasive water jet cutter, which is a 5 by 10 foot machine that we have in our warehouse across. This machine can cut wood, composites, plastics, and aluminum. Aluminum is about the strongest material we would cut on here. Our abrasive water jet cutter can cut titanium, hardened steel, kind of the whole deal. And we have, again, a 13,000 square foot warehouse across the street. We're starting to do the housing construction, the cars, that kind of thing. And so we can scale with different types of machines. And as I'll show you, we're starting to use these machines to build other machines. So if we needed a 20 by 10 foot milling machine, we could actually make it.
Cool.
And then kind of go from there. 3-axis milling machine, except this one with a smaller build area, we can get much higher precision and repeatability. So for example, we can do better than 10,000th of an inch accuracy on this. And so we can make our own electronic printed circuit boards in here.
Wow.
So we have, you know, just an inventory of this copper-clad laminate material, and we can go on the computer, design an electric circuit, lay out the board, send it over to this machine, which will mill out everything except where we want the traces to connect. And then we'll have our own electronics board without going out. We can go next door, solder all the components, and then program it without leaving the space. Go from, gee, I wish I had a microcontroller to control a greenhouse to a working product, including all the programming and like involved. So we use this a lot for electronics work. Also, we use machinable wax. So we can make kind of silicon soft tooling that we can then do molding and casting with. So if we wanted to make 20 of something, we could make a mold for that and then continue to replicate it from there. Those are the primary uses, but some people use it for jewelry making and some other things. It's a precision small thing. Behind you is a laser cutter and engraver. So I think it's making swag, coasters. Some of you will probably walk out with. And so that we use for a lot of prototyping work. Like out there you see a scale model of a conceptual exploration of a 400 square foot tiny house. Wow. So that was all cut on the laser cutter. But if you scaled it up to full size, the largest piece on there can be cut on the shop line. So we can conceive of larger projects, build scale models, work out the kinks before we go to the expensive materials on the other one. You probably recognize this as a wine model holder. So you can take materials and add value and come up with, product ideas, and I like to kind of go with that, right? So it's a stepstone to a lot of entrepreneurial work. Some of the students will do graphic work and engrave water bottles for a nonprofit to give away at their annual meeting, and have those purchased. So you say, okay, I can buy a $2 water bottle and create a $20 promotional item. I see how this process is working, and that's a stepping stone into the process of kind of understanding how to create value. It's not just about the commercial transactions, it's about understanding that you get rewarded by creating value some kind of way. So you can start out with the financial transactions and then start into other more subtle ways of doing it. Then there's a vinyl cutter over there. So this thing has a spinning bit that carves away material. That has a laser that vaporizes or burns away material. This has a blade that drags and just cuts the material. So kind of 3 different ways of fashioning things. And so the graphics on the door were made with a vinyl cutter, for example. That's a classic use for it. But we can also cut a copper foil material like this on there. And I can use this to make flexible circuit boards that I can stick to something else. But I can also make microwave antennas with this. We can make sensors with this. Because if I cut this into a shape that has a set of fingers and then separate it from another shape below it with some material that squishes, you can make a force sensor. The electrical characteristics between those will change when you add pressure to it. So we subvert the use of all of these machines for initial commercial intent, but the point was to have the technologies available so that you can really understand what the underlying mechanics are behind all these things that we use and actually start creating and innovating, creating different ways to do them. But this was actually this is a room where folks do the electronics work. And so, like the boards that we will mill on the other room, we have stock of all standard electronic components here. And we teach people how to actually hand produce circuit boards that are usually produced with automated equipment in other places, which is one of the reasons we can produce our own electronics here without having all sorts of expensive tools along those lines. And so we have microcontrollers of all different speed ranges. We have sensors that can measure temperature, acceleration, light, humidity. We have things that can control the environment, motors and light emitters or whatever. So we can sense the environment in all sorts of different ways. We can measure and make decisions about that, and then we can influence the environment in all sorts of different ways. And that's what control systems are about, right? We make radios. We've made kind of a handheld Wi-Fi Skype phone that some folks actually use in South Africa as a way to communicate effectively. You can do that whole thing, and we have done that whole thing in here, soup to nuts. The case, the electronics, the antennas, kind of the whole deal, right? But also behind you is a little controller for a greenhouse, and so that measures water temperature and air temperature, controls pumps to keep those in the range and the like, and all of that was made in here. And so again, it's the Fab Labs were designed so that you can, without leaving the space, basically go from a gee, I wish I had to a working product. We teach programming, we teach networking, we teach communications, in addition to the electronics, molding and casting. Programming, we teach it on the little teeny microcontrollers that go on those boards and on the host and communications between them. So we really cover the whole spectrum of things that's necessary to make the kind of products that you see on a regular basis. But bringing that to within the capabilities of just being able to do it here without any high capital equipment investment for tooling, and everything here can be different piece to piece because it's all computer numerical control. And so you can iterate quickly and evaluate ideas and zoom in on something that really suits a purpose effectively. Behind you is one of the prototypes of that milling machine I was talking about. And so that is actually made out of recycled milk bottles. It's high density polyethylene. You can actually buy that material in a restaurant supply store. It's cutting board material. You can buy it in yellow for poultry and green for vegetables and red for red meats or whatever. That's just the non-dyed version. But it's precision cut, so it snaps together and self-aligns. And so the parts that we actually have to buy add up to $550 to $600. And that does as good a job as a $9,000 commercial milling machine. So that's an early example of using the equipment in the lab to replicate the equipment in the lab. Within about 2 years, we'll be able to make a whole lab using the equipment in the lab, with that having the baseline capabilities of replicating itself. And so driving the cost down from about a $300,000 investment to about a $40,000 investment, which changes a lot. And when you're building the machines, you have the option of making them in ways that make more sense. Like that, uses recycled materials. Doesn't have nearly as much embedded energy as all of the metal in the other one, etc. So when you take control over not just making stuff, but making stuff that makes stuff, you can have a fundamental impact on the whole life cycle cost of things. And we can choose things that don't, impoverish any community from the extractive mechanisms that are necessary to get the materials, or diminish any community from the waste processes and waste streams that are necessary to dispose on this stuff, because we can design in reusability and all those pieces along the way. So all of this equipment can be used as stupidly or as intelligently as one wants to. The point is to have it under our control so we can apply our sensibilities to the process and actually have the means to make that work, right? Not just suggest to someone else that you might want to do that, but to just do it, right? We make our own Arduinos here. So you can buy an Arduino for maybe $40. We can make one for about $6, and then you can embed that.
Raspberry.
There are Raspberry Pis behind you, and we can also make our own version. We can also make our own version of a Raspberry Pi. And there's another step above that, which is Beagle boards, and we can make our own version of that also. So it's useful to allow people to understand what you can do with it just using a plug-in board. But then when you can stop buying a commercial thing and customize something yourself, that's another layer. So you can keep lifting the hood, peeling the onion, until you get all the way down to the base capabilities. And you can enter in whatever point makes sense and then go up or down as suits you. Right? Outside of that, we actually saw a picture. Somebody in the Netherlands did a design very close to this. And they said it was open source, but they didn't release the designs. We just looked at the picture, drew it up on CAD, fabricated it, and we had to buy it. And so we customized it. This is actually leveraging off of some of the work that we do with students in international knowledge transfer. So every year, sometimes twice a year, sometimes every other year, we'll train a group of students in some technology that's appropriate to collaborate with overseas. We've done it in South Africa, in the area around Pretoria. We've done it in Durban. We've done it in Soshangobe. And we also have done some in Ethiopia. And so one of the things that we do is renewable energy solutions. And so we started out with suitcase scale systems, and then the next one was a cart size, and the next one we did in Ethiopia is actually a building scale system. I think I talked about it a little bit this morning in terms of impacting infant and maternal health by providing electricity to rural health clinics that do a lot of the heavy lifting in that area. So one of the things we did is design a small system which they can produce, which allows them to service a market niche which is that everybody's not on the grid. So a lot of people have cell phones, and a lot of people have worked out very ingenious ways of powering their house, like on car batteries, but you need a way to charge all those kind of things. So if you have a solar charging station, you can go set up shop. Somebody can come and give you a small amount of money to pay for your operation. There's also a significant benefit for them to be able to do it in their immediate area rather than trudging this thing long distances. With a very small unit, you run out of capacity because the sun's not charging as fast as people are trying to get charged up. So you have the ability to serve maybe a couple of micro markets a day. The large cart-based system has much more capacity, but with the unimproved roads, you can still only push it to about 2 micro markets in the course of the day. If you stick it in the bed of the cargo bike, you can deal with about 8 to 10 micro markets in the course of the day. So this gives you an opportunity to expand the range of services that you offer and also make your own operation